Good day, everybody. Welcome to part 2 of the Midterm Exam Reviewer for Electronic Circuits Devices and Analysis. Today, we'll be covering the different BJT configurations, namely fixed bias, emitter-bias, voltage divider, collector feedback, emitter-follower, common base, and miscellaneous. We're also going to explore the following techniques: Ohm's law shortcuts, Kirchhoff's laws, KVL and KCL, node voltages, the reflected resistance, rearranging known formulas, common approximations, and algebraic manipulations. So let's start by going into detail what's into this video. So in this video, it's a continuation of part 1, and if you haven't watched it yet, you could open up my channel and look for this video. And also for part 2, we're going to focus just on these 6 configurations because unfortunately, due to time constraints and a lack of solved examples in our book, I can't really teach multiple BJTs at the moment. But rest assured, these 6 configurations will teach you almost everything you need to know to solve multiple BJTs. And if you have any questions or would like to share some of your computations for the multiple BJTs, you can do so on Messenger. So as always, we're using conventional current flow. And if you're ever looking at other examples from the internet, you need to know if they're using conventional current or electron current. So let's proceed to BJT configuration formulas using Kirchhoff's voltage law. So heads up, the formulas part of this video focuses on a re-explanation of our existing lecture. If you're looking for new practice problems, you can proceed to the chapter test by looking at the timestamps in the description. So let's proceed. There are 6 BJT configurations, and it's important that we familiarize ourselves and know how to identify them. So the fixed bias is very easy to identify. It's the most basic one, where it resembles the normal amplifier circuit, except there is no more VBB. There is only one voltage source, VCC. That's why we describe the bias as fixed. For the emitter bias, it's just the fixed bias with a resistor at the emitter. For voltage divider bias, it's just the emitter bias, except we have an additional branch here. So RB is R1 now, and the second resistor along the base is now R2. For collector feedback, the base directly connects to the collector, but not at the VCC. It connects here in the middle between the BJT and the resistor. So there is a bit of feedback going on in the collector. Next, for the emitter-follower, we are now following the emitter, as in the voltage that we reference is now in the emitter, and we can also measure the output voltage here. Lastly, we have the common base, where the ground is connected to the base, and then the base serves as the center for the emitter and for the collector. So first, we have the fixed bias configuration. It's characterized by a fixed bias where there's only one resistor RB connected between the power supply VCC and the base to establish a constant IB. It has a high sensitivity to beta, a poor thermal stability or thermal runaway, and has a fixed base current IB. So that's why this is the one that's most commonly modified. So the DC supply, VCC, is connected directly to RB and to RC. It releases the linkage between the two to the base current IB. Also, the bias voltages can be used to represent the DC supply for analysis purposes. So when we separate VC into VBB and VCC, that is when we will have the amplifier circuit that we had in the last part of the video. So here are a few formulas that you need to know. So the base current via KVL, so you start from VCC and encounter a voltage drop at RB and encounter another voltage drop at VBE. And then you get to the ground. So if you're going to use Ohm's law as reference, you can see that the total voltage is equal to VCC minus VBE. And then the total resistance is just RB. From our previous discussions, we know that IC is still equal to beta IB, and that VCE is equal to VCC minus ICRC. So another way to write VCE is VCE is equal to VCC minus V sub RC. So let's have an example here. So let's determine the following for the fixed bias configuration shown on the screen. So first, we're looking for IB sub Q. So if you see Q there, it just means quiescent, or it's at the Q point where there is no input signal yet. So since there's no input signal mentioned in this problem, in this problem, you don't really have to worry about the Q. Just treat it as it was IB. So IB is equal to VCC, and then we stop here because this is where the resistor is. So we're looking at the voltages here and here. So the voltages are 12 and 0.7 along the base emitter junction. So dividing that by 240 kilo ohms, we get 47 microamperes. We do the same for IC as last time with beta times IB, we get 2.35 milliamperes. For VCE, it's also the same as last time. It's VCC minus ICRC. So the explanation of that is from the collector to the emitter, we have VCC minus the voltage drop across this resistor. For VB, which is around here, it is going to be the same as VBE. Now here is something I want to clear up from the last video. VBE and VRB are different. So VRB is the voltage at the resistor. Meanwhile, VB is here, the voltage at the base, near the BJT. Similarly, we have VC is equal to VCE equals 6.83 volts. So VC is equal to VCE because from here, VC minus VE is just VC minus 0. So that's basically 6.83 volts minus 0. So that's why these are the same. Similarly, we also have VBC. So VBC starts from B going to the collector. So normally we're used to VCB, right? So VBC is just going in the other direction. If ever you encounter something with double subscript notation that you're not familiar with, just remember the first letter is positive and the second letter is negative. So B minus C. So that's really it for the fixed bias configuration. It's just a recap of what we had last time. Now the fixed bias configuration has the same rules of saturation as the amplifier circuit we had last video. So it's still VCC over RC because VCE is assumed to be 0. So you can just take a look at this slide if you want to refresh yourself with what's next. So here, for transistor saturation, the maximum collector current flowing through the load when the transistor is fully turned on, where VCE is equal to 0.2 volts or just assumed to be 0. So via Ohm's law, we just have VCC over RC. Next, we have the minimum base current via beta definition, where beta IB minimum is equal to the saturation current. So you can rearrange this if you just want IB minimum isolated. For the load line analysis, here is okay. So here is a clarification. So the reason it is VCE is equal to VCC minus ICRC is because the voltage across the CE region is the bias voltage minus the voltage drop at the collector resistor. So you might notice here, I put it as VRC to show it is at the resistor. Because in some circuits, VRC and VC are different. So VRC is across the collector, is the voltage across the collector resistor, and sometimes VC is a point after the resistor. So in the case of fixed bias, they're equal because VE is equal to 0. But know that in other configurations, that's not always the case. So if you are in cutoff, where there is no current at all, that means VCE is at a maximum. So it's just going to be equal to VCC. And if IC is at a maximum, then that is just saturation. So given this load line for figure 4.16 and the defined Q point, determine the required values of VCC, RC, and RB for a fixed bias configuration. So first of all, looking at this graph, there is no label for VCC here. But how did we get the value of 20? Well, recall that um, this part is the cutoff in the load line analysis. So as you can see, the vertical value is 0, so there is no current. However, there is a VCE value. That's where we got VCE is equal to VCC is equal to 20. So solving for IC, we have VCC over RC. So this is the saturation current. Now, since we are required to look for RC and not IC, we must swap places. So RC is equal to VCC over IC. 20 volts over 10 milliamps is equal to 2 kilo ohms. So this is our RC. Next, we do the same for RB, where we start with the IB, because this is where we can get the value of RB from. We already have a VCE, we already have a VCC, and we also already have a VBE. So remember, in the last discussion, IB is equal to VBB minus VBE. But here, VCC is going to be its voltage source because it is now in the fixed bias configuration. So doing the same steps as earlier, 20 volts minus 0.7 over 25 uh, microamperes is equal to 772 kilo ohms. So now let's proceed to the emitter bias configuration. So it's just the fixed bias configuration with an added emitter resistor. So now it's time to introduce a new concept called the reflected resistance. So recall that the current across the emitter is equal to the current across the collector plus the current across the base because they're both going in this direction. That's where we get IE is equal to IC plus IB. However, IC is equal to beta IB. So if we substitute beta IB plus IB is equal to IE, there is a repeated appearance of IB. So beta IB plus IB can be factored into beta plus 1 times RB. And then when we divide, rather, you don't need to divide it yet. But what you need to know is that IE is equal to beta plus 1 times IB. So if you remove this, it's just going to be IC is equal to beta IB. If you add the plus 1, it's going to be related to the emitter. So that's why in the reflected emitter resistance, there is always a beta plus 1 term beside the RE because it is the equivalent resistance of the emitter resistor RE as seen from the base side. So here, let's apply the base current via KVL. So we start with VCC. We encounter a voltage drop at IBRB, another voltage drop across the BJT, and another voltage drop across this resistor. So by the way, this is how it connects. So remember, KVL must always be in a closed loop. So usually the closed loop has the voltage supply and the ground. So rearranging the parts of this formula, you can have IB is equal to VCC minus VBE all over RB plus beta plus 1 times RE. If you're having trouble remembering this, just know that you have the voltage source minus this voltage drop. And then you have a resistor and then another resistor. So if the resistor is not directly connected to the base and you are solving for the base, you must add beta plus 1 beside it. So here is another set of formulas. VCE is equal to VCC minus ICRC plus RE. So if you notice earlier, it was just ICRC, and now it is RC plus RE. The reason why is because this is the path VCC, sorry, uh, VCC minus ICRC minus IERE. So the reason it is grouped together is because there is only one current through the loop. So we can write IC parenthesis RC plus RE instead of having one current for one current for the collector and one current for the emitter. So again, this is just one path. It's just one current. So next we have the collector voltage by voltage definition. So VC is equal to VCE plus VE, which came from VCE is equal to VC minus VE. So we just rearranged it and then we substitute it. So now we know that VC is equal to VCE plus ICRC. Next, we have the base voltage by voltage definition. This is just another one. VBE is equal to VB minus VE. We also know that it is VCC minus the voltage drop at the base resistor. So the base voltage by voltage definition, VBE. Okay, so it's just this one. VCC minus the voltage drop at the base resistor. Last one, we have the maximum collector current via Ohm's law. So since we now have RE, just remember that it will be included in total resistance now. So it will be RC plus RE. Basically, you always include RE beside RC. And then, if you are computing for something in terms of the base, add beta plus 1. So here, in the emitter bias configuration for figure 4.23, let's determine the following. So IB is equal to this. So this is a lot to recall, but let's see why is it like that. So again, VCC. So this is the voltage source, and this is a voltage drop. So that is for the numerator. RB, it passes through this resistor, and it also passes through this resistor. Since RE is reflected, we must add beta plus 1. So substituting everything, we get 40.1 microamperes. For IC is equal to beta plus IB, it's still the same. For VCE is equal to VCC minus ICRC. We now make sure that the RE is included. Now, why do we not include the beta plus 1? It's because we're not computing for the base. We are already at VCE. So it's not related to the base. That's why there is no beta plus 1 beside the RE. So again, RE is usually paired either with the beta plus 1 if it is for the base, and RE is added to RC if they are going on the same path. So next, VC is equal to VCC minus ICRC. So basically, uh, it is just saying what is the voltage here minus the voltage here. So that is why it is VCC minus ICRC. So again, ICRC can be rewritten as VRC. Again, VC and VRC are two different things. Next, we have VE is equal to VC minus VCE. So this is just rearranged from VCE is equal to VC minus VE. So it's just rearranged. For VE, we have, okay, so VE is here. And then notice that it is connected to ground. So whatever VE is just going to be the same. So VE minus 0, that's still going to be VE because it's connected to ground. Also, the current across E is the same as the current across C. Why? Because again, it is connected to the ground. VB is equal to VBE plus VE. So this is just rearranged from VBE is equal to VB minus VE. Next one we have VBC. So again, VBC, it's not the usual thing that we are solving for. But remember, uh, if you have something VB and C, that means it's just VB minus VC. So let's proceed now to the voltage divider bias configuration. It's just the same as the emitter bias configuration, except the RB before is now considered R1. And now we have an additional resistor R2 connected to the ground and to the base. Remember, R2 must be connected to the ground. So because there are now two resistors, we now need to use the Thevenin resistance. So this is the formula we had last year. If R1 is parallel to R2, then if we redraw them as only one resistor, like this, it's going to equal 1 over R plus 1 over R2. And then whatever the result of that is, we have to get the reciprocal. Next is the Thevenin voltage. Since the voltage is now in parallel, so VCC is connected to VR1, we must use this formula. So the Thevenin voltage is equal to VCC times the voltage divider formula. So we're going to use R2 for the numerator and R1 plus R2 for the denominator. If you're wondering, can I use R1 instead of R2 for the numerator? The answer is no. Again, you need to use R1, sorry, you need to use R2 specifically because it's connected between the base and the ground. Next, the KVL loop voltage. So we start with the Thevenin resistance, sorry, the Thevenin voltage. So assume that there is a voltage source here. Thevenin voltage minus the voltage across the base resistor. Since there is no base resistor, we need to use the Thevenin resistance minus VBE. So across this BJT minus the voltage across the emitter resistor. So again, if you want to rearrange it just like last time, remember the numerator for I sub B is going to be the source minus the drop. And then the denominator is going to be the base resistor, or in this case, base resistors, plus RE as seen from the base. Again, RE as seen from the base. That's why we have B plus 1. Last one for this slide is the voltage across the CE region. This collector is directly connected to the voltage source VCC. The emitter has the same current as the collector, which passes through the collector and the emitter resistors. So again, it's just the voltage source minus the voltage drop here and here. IC is just going to be the same as IE because it is just going in the same direction. Now, when are we supposed to use approximate analysis? So earlier, we had the exact analysis. So we are allowed to use the approximation if this condition is met. So if beta times Re is greater than or equal to 10 times this resistor, then that means the effect is so small that we can just approximate instead of being exact. So again, beta Re has something to do with the reflected emitter resistance. So again, if R2 is so big or so influential that it is bigger than the reflected emitter resistance, we can just approximate. So what changed? Earlier, we have VB is equal to, okay, so we did not have a direct value for VB. But as you can see here, I said earlier that VRB and VB are not the same. However, see here. So ETH, let's say ETH comes before the resistor. So there is a separate VB after. But if we are just approximating, we can just assume that VB and ETH are just the same. Again, that's an approximation. It's not supposed to happen because there's a small drop across the resistor. But since we are approximating using approximate analysis, we can allow it. So this basically allows us to skip the steps. Next, the base current is going to be negligible. Since both B and IB aren't calculated, we know that the Q point is now independent of beta. So now that the collector current is computed, we can use the usual formula ICQ is equal to IE. So again, we ignore IB. So IE is now going to equal approximately to IC. So that's where the idea comes from, where IC is equal to IE. Lastly, the voltage across the CE region is the same. It's going to be VCC, the source, minus the voltage drop across here and here. And lastly, it is the same almost as the saturation formula we are used to. Just remember that VCC over RC becomes RC plus RE. Remember, there is no beta plus 1 beside here because there is already an RC and we're not observing it from the base anyway. So here's an example from the book, and the first thing I noticed is it used the exact analysis when we are supposed to use the approximate analysis. So to check this, you should see RE is equal to 1.5 kilo ohms. So multiplied by beta, that is 150 kilo ohms. However, when we have this R2, so R2 times, let's see, R2 times 10 is going to be 39 kilo ohms. So 150 is greater than 39 ohms. We should be able to use the approximate analysis. But what was used here is the exact analysis. Anyway, for the sake of illustrating what is in the book, let's continue with exact analysis. So RTH, or the Thevenin resistance, is what is here. So the equivalent of 39 kilo ohms and 3.9 kilo ohms in parallel is 3.55 kilo ohms. Next, we have ETH. So ETH is going to be the point here. It's basically what happens when we apply the voltage bias, the voltage divider rule to VCC. So 22 times the voltage divider rule, so that's going to be 22 times 3.9 kilo ohms over 39 plus 3.9 kilo ohms. That's going to equal 2 volts. So if this is 2 volts and this is 3.55 kilo ohms, we can now compute for IB. So remember that there is a voltage drop across this resistor. So that's why we have 2 volts minus 0.7 volts for the voltage. And then the resistance is going to be 3.55 at the base, but we must also include this. So RE is going to be 1.5 kilo ohms, and since we are observing it from the base, we must multiply it to beta plus 1. That's why the beta is equal to beta IB. That's why IB is equal to 8.38 microamps. So IC is equal to beta IB, and that is 0.84 microamps. Milliamps, sorry. Lastly, we have VCE is equal to VCC minus RC, parenthesis RC plus RE. So that's from VCC, the source, minus the drop here at 10 kilo ohms, and the drop here at 1.5 kilo ohms. So the drop is multiplied to the current IC, which is the same across the collector and the emitter. So that gives us 12.34 volts. So another example. Now let's provide some more emphasis on exact versus approximate analysis. So again, RE is 1.2 and we multiply it to 50. And then 22 kilo ohms must be multiplied to 10. So as we can see here, the correct approach is that we use the exact analysis because it's not satisfied. So again, we get the Thevenin resistance, the Thevenin voltage, the current across IB, and then the current across IC, and then the voltage across C and E. So it's the same as the last item, so I'm not going to discuss that anymore. But now, let's see the difference if we have approximate analysis. So using approximate analysis, we see that the Thevenin voltage we computed earlier, 3.81, is going to be the same here and the same here. So again, that's what I meant by ETH and VB being two different measurements. However, if we're approximating, then we are ignoring the voltage drop across the resistor. That's why VB is approximately equal to ETH. So from here, if we know VB, then we know what VE is. Because if this is 3.81, we just subtract 0.7 voltage drop, and this will be 3.11. So that is how we get the shortcut. So ICQ is equal to IE is equal to VE over RE. So basically, it's saying this. It's the same here and the same here. So IE is equal to the voltage over this resistance. So if we solved earlier that 3.11 volts is the IE, then we have 2.59 milliamperes for the IE. So that's also going to be the same here. Lastly, we have the VCE, where it is VCC minus RC and RE multiplied to the current. So next, let's go to collector feedback. We start with the emitter-bias configuration, and let's improve the stability by introducing a feedback path from the collector to the base. So the sensitivity to changes in beta or temperature variations is less than encountered for the fixed bias or emitter-bias configurations. However, the voltage divider is still the most stable. So because of the feedback path, RB is replaced by RF. So again, the resistor is no longer here. It is now up here. And that B plus 1 RE is now replaced by beta RC plus RE because the path that the current goes on has been changed. So again, to illustrate what I mean by the current goes in a different path, let's see here. Using KVL around the base emitter loop, you have VCC minus I prime C minus IBRF minus VBE minus IERE is equal to 0. So as you can see, we went from uh, the source to the ground. You should know that I prime C is not the same as IC, but we approximate it anyway for the purpose of simplicity. So when we substitute that, we can substitute IC is equal to beta IB. So this one becomes beta IB, and then we can use this beta IB and this beta IB. We can factor it out and then use it to uh, arrive at this equation. So I'm not going to show the full equation because it's long, but I will show you an easy way to remember this formula. So we have VCC minus VBE. So source minus the drop. And then RF is going to be the resistor along the base, and RC and RE are going to be the resistors not at the base. So for the resistors not at the base, you must multiply them to beta. Again, remember, just use beta and not beta plus 1. So again, for the collector emitter loop, we do the same thing. VCC minus IC RC plus RE. So again, it's the same as earlier. IC is the same current flowing through RC and RE. The saturation condition is the same also. It's VCC all over RC plus RE because again, they are on the same path. So let's determine the quiescent levels of IC and VCE for the network of figure 4.41. So again, what I can see here is that this is our VCC, and then we have a voltage drop here. That's why it's 10 volts minus 0.7. And then for the RF, 250 kilo ohms is along the base. That's why we can copy it as is. But for the 4.7 and the 1.2 kilo ohms, it is not connected to the base. That's why we have to multiply it by 90, which is the beta. So substituting all of that, we get 9.3 volts over 781 kilo ohms is equal to 11.91 microamperes. So if you see IC sub Q, just assume that it is IC since there is no input signal given. And then you can substitute beta is equal to IB to get this value. Lastly, you have VCE subscript Q. So that's VCC minus IC times RC plus RE multiplied to the current flowing between them. So again, this is the same. So you can just group them under IC. That is how you get 3.69 volts. So the collector feedback configuration is relatively easier compared to the voltage divider bias configuration. It's just more like the fixed bias and the emitter bias. So let's have another one. What if there are two resistors along the feedback loop? The feedback branch. Then it's simple. You just represent it as RB. So RB is simply equal to RF1 plus RF2. It's just changing the way you label it. So again, VCC minus the drop, and then you have the base resistors copied as is. So that is 91 plus 110, and the resistors that are not at the base. So that is 3.3 kilo ohms plus 0.51 kilo ohms. Remember, before you add them to the calculator, make sure they are the same unit. And then you multiply it to the beta, which is 75. That is how you get 35.5 um, microamperes. IC is equal to BIB as IC is equal to beta IB as always, and you will use that beta IB. You use the IC to get this VC. So this time, um, remember what we usually have is VCC is equal to VC minus ICRC. So I want you to look here. VCC is, I think it's at this part, or rather at this part. So it's going to be the difference from VCC minus um, the thing across the resistor. Actually, wait. Let me redraw it. VCC is here, and the resistor is here. So whether it's located here in the middle, ideally it's right here, or sometimes it can be illustrated as here. Know that there is a source minus a voltage drop. So it's the same idea. So that's 18 volts minus, yeah. So it's 18 volts minus the voltage across this resistor at the collector. And that's how you get 9.22 volts. So for the emitter follower, it's similar to the previous configurations except that the output voltage is measured at the emitter leg. So if we are to look at our example from earlier, V sub O, or the output voltage, is measured here along the collector. This time we're measuring it along the emitter. So let's look at the base emitter loop. So for this first equation of KVL here, we have negative VEE plus IERE plus VBE plus IBRB is equal to 0. Now you might be wondering, why are we using plus across the voltage drops? It's because we're starting at a negative voltage. So if you wanted, you could also go in this direction. VEE minus, sorry, rather, yeah, VEE minus IBRB minus VBE minus IERE. So again, sorry, this is a typo. This should actually be a negative sign. But anyway, regardless of which KVL you do, here is the formula for the base current at the base emitter loop. So IB is equal to VEE, the voltage source, minus the voltage drop, all over RB, which is copied as is because it's at the base, plus the resistance at the emitter, as seen from the base. So again, if it is as seen from the base for the emitter, you need to include beta plus 1. Now for the collector emitter loop, the first KVL here. So VEE plus IERE plus VCE is equal to 0 if we're going in this direction. Now again, if you flip all of the negative signs, you're going to end up with this one. Whichever one you are using, you should know that VCE is equal to VEE minus VEE minus IERE. So from basically source minus voltage drop. Now you may be wondering, what about VC? Well, as you can see here, VC is connected to the ground, so that's going to be 0. That's also why VCE is equal to just VE, because again, it's connected to ground. So determine VCEQ and IEQ for the network of figure 4.48. So let's see. Let's apply our KVL. So starting here, we have VEE plus IERE plus VBE plus IBRB is equal to 0. So if you rearrange that formula, we are going to get here. You can remember that by having the source minus the voltage drop all over RB plus RE as seen from the base. So that's how we get 45.73 microamperes. For equation 4.45, VCE is equal to VEE minus IERE. Again, because VEE is at 20 volts minus the voltage drop here. So again, you could do it either in this direction, clockwise or counterclockwise. And also VC is equal to 0. That's why we're just having VE. Anyway, that's how you get 11.68 volts. If you want to get the current across the emitter, you can just use the current across the base times beta plus 1. Again, the plus 1 is important because that is what we established earlier from the other KVL formulas. So the last configuration we have defined is the common base configuration. It's unique such that the input signal is connected to the emitter terminal and the base is at ground potential. So again, the input signal is coming from here. So our current is actually going this way. And then we have the current going here. And then this is going in this direction. Yeah. So this configuration provides a very low input impedance, high output impedance, and a good gain. So starting from the source voltage at the emitter, there is a voltage drop across the BE junction and an emitter resistance. We can rearrange the formula to solve for the emitter current. So again, remember, source minus drop over resistance. For the base collector loop, we have VCC minus the drop across the resistor minus VCB is equal to 0. So VCB is equal to VCC minus ICRC. Again, source minus a drop. Last for this slide, we have the voltage across the CE region by KVL. So the CE region is this one, and we're essentially ignoring the middle part for now. So we can start from VEE plus VCC minus the drops here, here, and here. So this is our emitter collector loop. So the drops are at RC and RE, which have the same current, which is why they are grouped as shown here. As for VCE, that is what we are solving. So you can just rearrange this formula to find VCE. So for the common base configuration, determine the currents IE and IB and the voltages VC and VCB for the common base configuration shown below. So we start it, I sub E is equal to VEE minus VBE all over RE. That's how we get 2.75 milliamperes. For IB, we have to use the relation shown earlier, where IE is equal to IE is equal to IB times beta plus 1. So dividing both sides by beta plus 1, we have this formula. And that's how we get 45.08 microamperes. For VCE, again, VCE is equal to VEE plus VCC minus the drops at the collector and the emitter resistors. So that's how we get 4.1 volts. For VCB, So again, C is from here going to the base. If you want to find this, just use KCL. So VCC minus the drop here, that will give you, okay, wait. So let's see here. VCC minus ICRC is what we got from the KVL. So it is also equal to beta IBRC. So since again, we don't have the IC yet because it's not solved here, you can solve it first. So beta IB is going to be 45.08 times the beta, which is 60. So it's up to you if you want to separate the explanation for it or just put it straight into here. But in the end, that's how you get 3.51 volts. Now, the reason I kept on emphasizing how to get the formulas rather than the numbers that are on the screen is because the miscellaneous bias configuration needs a combination of all of those ideas at once. So here, for the network of 4.53, this one looks like, um, yeah, this one looks like, what is it called again? Okay. This one looks like a collector feedback uh, configuration, except there is no resistance here. So earlier, if we had beta times RC plus RE, this time there is no RE. That's why the formula just becomes like this. So aside from that, there are not really any other modifications. Just assume there's no RE, and this example is basically done. So just continue this example like you normally would. So IC is equal to beta IB. VCE is equal to VCC minus ICRC. VBE is equal to beta minus VE. So that's just gonna be VB minus 0. So that's just gonna be 0.7. VCE, again, C is somewhere, I think, here or here. VC is going to equal to VCE because the emitter is at ground. And as you can see here, VE equals 0. Lastly, VBC, so going to the base to the collector, you just get this one minus this one, and you get negative 10.56. Now, you should know that if you see a negative sign, you can double check it. Don't just ignore it in your final answer because sometimes it's important. So, based on the characteristics that we described earlier, we know that the currents are going this way, and this way. So naturally, if we are going to get a voltage going in this way, it's going to be negative. So don't erase the negative sign in the final answer because you will need it. For this one, example 4.19, determine VC and VB for the network shown below. So let's analyze. I don't really know what kind of. Okay, wait. It looks like a fixed bias to me. There's a fixed bias, except the voltage is not here anymore, but rather it's here on the bottom. So I think since I don't know the pattern for it, the safest bet is to just use KVL. So using the clockwise direction for the base emitter loop, so the base is here and the emitter is here. We can connect it this way. First we have, okay, so again, the KVL is going to be negated because we have a negative source. So 9 or VE plus this voltage drop of VBE plus this voltage drop of IBRB is going this way. And then we can just negate it again. Or we could just do it in the clockwise direction. VEE minus IBRB minus VBE is equal to 0. So just rearrange that and solve for IB. So you already have VEE, VBE, and RB. So just substitute that and you should get IB is equal to 83 microamperes. Substitute that into IC is equal to beta IB and you get 3.75 milliamperes, or just 3.8. Now here is something interesting. VC is equal to negative ICRC. Why? So again, let's see. Where is our VC? It is somewhere here. VC is equal to negative ICRC because IC is going, let's see. Okay, IC is going in this direction. And our RC is here. So it's negative because if we are using this flow of current, following conventional current, we are actually using positive, or in this case, 0 goes to negative. So our direction is going this way. That's why VC is shown to be negative 4.48. Also, it makes sense because if our VC is here, we have a negative value and this is 0. Then that means the current is flowing this way. If our VC was positive, like positive 4, and then it's going this way, it is not following it is not following the current anymore. So that's why this is correct. We have a similar thought process for negative IBRB. So this point, VB, is going to be, yeah, it's going to be negative because if this is negative, it means, let's see, 8.3. So negative 8.3 is more positive than negative 9. So that's why it is going this way. We also have 0. So if 0 is going to negative 8.3, then 0 going to a lower value is also correct. So again, if you have a negative voltage source, always check the direction of your voltages and currents. So last one, for the one in our lecture that is the most difficult, we have the miscellaneous bias configuration that looks like a voltage divider, except there is a VEE that is negative 20 volts instead of a ground. So first, the main concept we want to get here is that focusing on the base, we have VB here, RTH here, and ETH here. So again, you need to understand that ETH comes before the resistor and then you have the VB. Now, in order to get to what I just described, let's first solve for RTH. So RTH is going to be the equivalent resistance between these two. So these two are in parallel. So you have 8.2 kilo ohms in parallel with 2.2 kilo ohms. That equivalent is 1.73 kilo ohms. So now that we're done with RTH, let's now proceed to I and to ETH. So if you can see here, we can draw KVL from here down to here because this is positive to negative. So that way you can expect that the currents are meant to go in this direction. So the reason we have VCC plus VEE all over R1 plus R2, so this part that I just drew can be redrawn like this. So starting from 20 volts, there is only one current passing through R1 and R2. And then this negative 20 is going to become positive 20. Why? Because if we are going in this way and this is positive 20, then that means the voltage sign is done like this. And since this is negative, usually the voltage source, if it is connected like this, it's going that way. But since we are going in this way with the current, we are negating negative 20, which is how it becomes positive 20, as seen here. Basically, we are drawing it like this. And then all of that can be closed if we put an imaginary ground. So this is the equivalent here. So solving for I, you know that there are two sources, VCC and VEE. So that's why they are VCC plus VEE. Also, you have R1 plus R2 because they are in series. So solving all of that, you get 3.85 milliamperes. Next, you have ETH. So remember, ETH comes before the equivalent resistance. So that means our ETH will be somewhere along here. So if our ETH is somewhere here, let's consider the polarities again. This is negative 20 and this is positive 20. So that means we are starting from high voltage at IR2 going down to VEE. That's why we have positive IR2 minus VEE. Yeah. Okay. Then we also have 3.85 milliamps times 2.2 kilo ohms minus 20 volts is equal to negative 11.5 V. So again, we got 11.53 going this way. However, if we want to use our voltage going in this direction, it must be negative. So again, if our current is going this way, but we are expecting our voltage to pass through RTH and the base, then it is only correct that ETH should be negative. So the network can then be redrawn as shown in the figure on the right, where the application of Kirchhoff's voltage law results in this. So basically, we have ETH, and since it is negative again, we are not going to draw it like this, but rather we're going to draw it like this. So we start with a negative voltage source minus a voltage drop across RTH, minus a voltage drop across VBE, minus a voltage drop across IERE, plus a voltage source of VEE. Or, if you prefer, you can go this way. So negative VEE, as I showed earlier, negative VEE plus this voltage drop, plus this voltage drop, plus this voltage drop, and then plus this one. So you need either way that you choose, either clockwise or counterclockwise, make sure that your voltages are correct because you should arrive at the same answer here. Now substituting IE is equal to beta plus 1. So here, you can replace it with this and then group the IBs together. So you can solve for the IB. Now if you don't want to do all that, there is another way. Since the IB is going this way, you know that things are going to go in this direction. So you have VEE minus ETH minus VBE. Since there's going to be a voltage drop here, and here. And then, this is in reference to VEE, by the way. And then you have also RTH. So the equivalent resistance is here plus the resistance that is not at the base. So as observed from the base, RE is going to become beta plus 1. So this part is a bit hard to do on a shortcut. I think this is the safer option if you have to solve something like this. So from there, only the first half is the hard part about this problem. Once you're able to get past this part with no problem, we are able to find IC, VC, and VB as normal. So IC is equal to beta times IB. VC is equal to VCC minus this voltage drop, and VB is equal to let's see, negative ETH minus IB RTH. So negative 11.53 minus the voltage drop across the Thevenin resistance is equal to VB, which is right here. Okay, so that's all for the lecture. So now it's time to proceed to the chapter test. So all the items I showed you so far are just from the lecture. So now it's time to proceed to new problems that I had the answer key to at the end of the book, and then I had to make the solutions myself. So for your information, this chapter test is from chapter 4 of Boylstad's Electronic Devices and Circuit Theory, I think. So here is a summary of the BJT configurations and their formulas if ever you wish to take a screenshot so you can follow along with the next parts of this video. So here, let's have the fixed bias configuration. So we are to determine IBQ, ICQ, VCEQ, VC, VB, and VB. So this is an easy one to start with. So first of all, for the first three given, when we say Q subscript or quiescent values, it just means that we can use the default formulas. There is no input voltage mentioned here, so you can just use the formulas as normal. So let's apply Ohm's law for IB. IB is equal to VCC minus VBE. So VCC is the source minus VBE, the voltage drop, all over RB. So IC is equal to beta times IB, and VCE is equal to VCE minus the drop across the collector resistor. And then we don't have to do anything with VE because it's connected to the ground. So VCC minus ICRC gives us 9.52 volts. For the node voltages, we can draw them here, or rather, they're already here, VB, VC, and VE. So the node voltages. Since VE is connected to the ground, we can say that VE is equal to 0. Also, if this across the silicon BJT is a 0.7 volt voltage drop, we have VB minus 0 is equal to 0.7, or simply VB is equal to 0.7. And lastly, for VCE, we just have VC minus E. So if CE has already been solved earlier, and this is 0, then that means this is simply 9.52 volts. So VCE is equal to C. So now we have another one. We are to determine IC, VCC, beta, and RB. So this is still a fixed bias configuration. So let's practice setting up our formulas before we do the solutions. So for the collector current, we know that IC is equal to IB. However, beta is not given. So obviously, we have to solve for beta first. Knowing that we do not have IC and we do not have beta, The next thing that we can use is the emitter current. So IE is equal to IB plus IC. And again, if we don't have IC yet, let's substitute it with beta IB. And then factor out IB from these terms. So we have IE is equal to beta B plus 1 times IB, which we will use later. Because we do know that we have IE and we do have IB. So if this is already given, then we can just substitute it to find the beta. Later on, we can also look for the voltage source. So from VCE is equal to VCC minus ICRC, we can swap the places around. So we can get VCE is equal to VCE plus ICRC. Again, this is the formula where it came from. Because across this region, we have VCC minus the voltage drop here. Later, we can also compute for the base resistance after we have already solved for the VCC. So you're going to need uh, VCC minus VBE over RB to get the base current. But since the base current is already given, you can swap places with IB and RB. So now we have already planned for all of the things. Now, of course, this isn't always possible, especially in tests when we are short on time. But if you can, or at least try to visualize it in your mind, which ones to solve first, it could save you a lot of time in solving the problem. So first, we have to compute for beta, and then for the collector current. So beta, from this equation, we know that IE over IB is equal to beta plus 1. And then move this plus 1 to the other side. So it will be IE over IB minus 1 is equal to beta. So substituting all of that, we see that beta is equal to 199. So multiplying 199 to 20 microamperes, we get IC is equal to 3.98 milliamperes. So this IC is what was missing earlier. Now we can substitute it here. So we have VCE is equal to 7.2 volts plus IC times 2.2 kilo ohms. So we know that the VCC is now providing 15.96 volts, or approximately 16. Lastly, since we know how much voltage is being dropped here, how much is being supplied here, and how much is flowing here, that means the only thing missing is RB. So now that we can compute for RB, let's apply the formula. So RB is equal to 15.96 minus 0.7 volts all over 20 microamperes. So that gives us the final answer of 763 kilo ohms. Now let's proceed to the emitter-bias configuration for chapter 4. So again, let's examine what happens when we approximate and we do not approximate. So for the purposes of our examination, I recommend doing this example because the answer key in the book says this is the correct answer. However, for our examination specifically, I recommend doing it this way. So the formulas. First, we are to determine beta. So beta is equal to IC over IB. So let's see. We are given IB and nothing else. We don't have an IC here, but it is easier to use IE because we already have 2.1 minus 0 all over 0.68. So we're going to use IE. So IE is equal to beta plus 1 times B. And if we rearrange it, we're going to get beta is equal to IE over IB minus 1. So this is the exact one. So at this point, I have reached until this point already. The emitter current I mentioned earlier is 2.1 volts minus 0 all over 0.68 kilo ohms, which leads us to 3.09 milliamperes. So if this one is 3.09 milliamperes, and we already know what our beta is, we can use this already. So beta is equal to IE over IB minus 1. So that is how we get the beta of 153.5. Now some books say that if beta is greater than 100, you can just skip the positive one and the negative one. Like you can just use this. But for the purposes of this problem, I'm going to assume that we need the plus one. So next, we have the collector current. Beta IB is equal to 3.07 milliamps. We also have the voltage source. So earlier, we also solved for the voltage source. So the voltage source usually comes from this formula. How did we get this formula for the emitter bias configuration? So in case you don't memorize it, here is something you can do. VCE is equal to the source minus the voltage drop here and here. Since there is only one current, IC is equal to RC. Sorry, IC is equal to IE. So you can just distribute. Sorry. So ICRC minus IERE is just going to be the same as this term. Since we're solving for VCC, just move all of this to the other side. So VCE plus the voltage drops is equal to VCC. So now we are at this part of the solution. VCC is equal to 7.3 volts plus 3.09 milliamps times 2.7 kilo ohms plus 0.68 kilo ohms. So that is how we get the voltage source of 17.68 volts. Lastly, we have the base resistance. So similarly to earlier, we need to use the base current to get the base resistance. So if you're looking to memorize this formula, IB is equal to VCE minus this voltage drop, VBE, all over RB, which is copied as is, plus the resistance at the emitter as seen from the base. Again, B plus 1. We're not going to use B, but we're going to use B plus 1 to be exact. So you can shuffle this formula, multiply this, and then isolate RB. You're going to get this formula. So VCC minus VBE is this part all over IB minus B plus 1 times RE. So following all of that, you're going to get the final answer of 743.94 kilo ohms as the base resistor. Now this is what I meant when we are using an approximation. So if you are going to check the answer key for this one, these are the answers. So what's different here is they use the approximation without the minus 1 and without the plus 1. And their beta is 154.5 compared to 153.5. So their collector current assumes that IC is equal to IE because the base current is negligible. So it's going to be 3.09 milliamperes, which they use to compute the voltage source. So because of that assumption, their answer is slightly higher than ours. It's 17.74. So because the voltage source is higher, their base resistor is also higher. So again, refer to your textbook and your lecturer's instructions for this one. But for my schoolmates, I recommend using it this way. Next, we have the voltage divider configuration, where we are to determine the quiescent values of IB, IC, and VCE, as well as the node voltages at C, E, and B. So this is our given diagram. So let's check the approximation condition. So beta RE 0.68 times 80 will be checked if it is greater than 10 times the beta RE. Again, for the approximation condition, we only use the approximation beta RE instead of beta plus 1 RE if we are using this approximation condition. And again, recall that R2 must be the one that is connected to the ground. So substituting all of that, we have this. The condition is not satisfied, so we are to use the exact analysis. So now that we know which approach to take, let's use the formulas. The Thevenin voltage, which will be around here, sorry, Thevenin voltage, which will be around here, will be source voltage times the voltage splitter rule. So R2 all over R1 plus R2. So substituting that, we have 2.05 volts. The Thevenin resistance, which should be around here, is equal to the reciprocal of this plus the reciprocal of this. After you get the sum of that, get the reciprocal again. That will be 7.94 kiloohms. For the base current, this formula is a bit hard to memorize, but just remember, for the base current, it is the Thevenin voltage minus the voltage drop all over the Thevenin resistance plus the emitter resistance as seen from the base. So that is how you memorize it. If you're not sure, you can do KVL, but it's time consuming. So substituting all of that, you have 21.42 microamps. The collector current, as always, is computed with beta times IB, so you have 1.71 milliamps. Lastly, the voltage across the CE region. So CE region, the CE region starts, sorry, the CE region has one current across RC and RE. And we start from 16-volt source going down to the ground. So that's why our formula is VCC minus IC parenthesis RC plus RE. Again, RE does not have the beta here because we're not computing with respect to the base. We're computing for the CE region. Substituting all that, we have 8.17 volts. So we continue the same item to look for the node voltages. So earlier, we stopped at VCE is equal to 8.17. So this is VCE. Since there is a resistor here, we cannot just assume VE is equal to 0 because this is supposed to separate the voltages from the ground. There's also a resistor here. So what we can do first is look at this one. So we know the node voltage of B is going to equal ETH here minus whatever voltage drop happens across the Thevenin resistor. So basically, remember ETH, resistor, and then VB. So knowing that, we have ETH minus IB times RTH from this base formula. We get 1.88 volts. So again, if you're confused where this comes from, it's just this formula, but we change the variables. Next, now that we know VBE and we know that it drops by 0.7 here, we simply have 1.18 volts. So basically, just subtract 0.7, and that is your VE. Next, since you have the VE and you already know VCE, then you can just rearrange it. So VCE is equal to VC minus VE. Rearrange that to solve for E. And you have 8.17 plus 8, sorry, 8.17 plus 1.18 volts is equal to 9.35 volts. So that is the end of this item. We have another voltage divider configuration where we are to determine IC, VE, VB, and R1. So this is different because normally we're always given the R1 and we're also used to having the IC. Well, not always, but you get my point. So if we're missing the R1, we cannot really determine if it is approximate or exact. So if beta is not given, then assume that you are going to use the exact. So the collector current. So the collector current is the first one we solve because it is the most convenient. We already have voltages on two sides and we already have a resistor in the middle. So solving this will give us more information. So 18 minus 12 over 4.7 kilo ohms is going to give us 1.28 milliamps. So the voltage across VE. So the voltage across VE is going to equal VE minus 0 volts over RE because this is connected to 0 volts or to the ground. So therefore, we can say that IERE is equal to VE. So again, for the voltage divider specifically, we have the same current. So IC is equal to IE. That's why you can substitute 1.28 here. 1.28 milliamps times 1.2 kilo ohms will tell us the voltage across this region. And since this is 0, then automatically whatever we solve here will also be the VE. So the base voltage. Now that we have the VE and we know that the voltage drops by 0.7 going this way, we know that the base voltage will increase by 0.7. So 0.7 plus voltage across VE is equal to 2.24 volts. Lastly is the resistance. So usually for the resistance, if that is what we compute first, now that is what we compute last. So let's see. This is the formula for the resistance. Now since we cannot really compute the Thevenin resistance here, we cannot really make it exact for everything. However, assuming it is okay for this problem, we can say that ETH is approximately equal to VB. So again, ETH is here and RTH should be here. But since it's not given, we have to make the assumption. So if we already have 2.24 volts for VBB, we already know VCC is 18 volts, and we already know what our value of R2 is, then that means this formula is ready for substitution. So I just rearranged it for you. And we have R1 is equal to VCC times R2 all over VB minus R2. So substituting all of that, we can see that R1 is equal to 39.4 kilo ohms. So this matches what is in the answer key of chapter 4. So now we have another one. This is a collector feedback configuration. So collector feedback is relatively easy. Just make sure that you remember the formulas. So this one typically has the same amount of given as a fixed bias. So you are to determine IB, IC, and VC. So just recall, if you're going to use KVL, you need to know where the current is going to pass through. So it's going to pass through here. So you have VCC as the source minus the drop all over RF, which is the resistor at the base. So since it's at the base, you can copy it as is. Just make sure that you label it RF to distinguish it from the formula that usually has RB, because this is a collector feedback. It's here. You also need to add the resistances of RC and RE as seen from the base. Again, we are computing for the base. So RC and RE must have a beta term. We do not use beta plus 1 based on the derivation of this formula from KVL. So it's not an approximation, that's actually just the way it is. So substituting all of that, we have 18.09 microamps. The collector current, as always, is beta times IB. We get 2.17 milliamps. And then the collector voltage can be acquired through the collector current. So again, IC is equal to VCC minus VC all over RC. So since we are solving for we're solving for VC, we must isolate it. We rearrange the formula to get VC is equal to VCC minus ICRC. We also know that VCC is 16 volts, 2.17 milliamps is equal to the collector current, and 3.6 kilo ohms is the resistor across the collector. Therefore, VC is equal to 8.19 volts. So for this emitter-follower configuration, we know that it is an emitter-follower 1 because we have an output voltage measured at the emitter instead of measured at the collector. So in this case, we need to find IB, IC, and RE, as well as VB, VC, and VE, as well as VB and VCE. So this is one of the longest ones so far, I think. But we have this. First, to determine, let's see what we can do. So there's only one voltage, there are no currents, and there are three resistances. So as we can see, there's not much information that we can have. We can set an RTH and an ETH. But since we have no other information, we can actually start this by assuming ETH is approximately equal to VB. So this is a special case where we can use this. And then we know that the voltage supply is 12 volts times the voltage divider rule. So R2 all over R1 plus R2. So substituting, we get 9.46 volts. So we assume that this is going to be 9.46 volts. And then minus the voltage drop for a silicon BJT, we have 8.76 volts at the emitter, which is here. So the collector voltage, as you can see, it's not really like a voltage divider completely because there's no resistor across the collector voltage. So VC is 12, VE is 8.76, and VB is 9.46. So now that we have our voltages, we can now start computing for the currents. So first of all, if we already have VE, which is 8.76 here, minus 0 volts across this 1.2 kilo ohm resistor, then we can say the emitter current is 7.3 milliamps. Knowing this, we can also say that the base current can be found using beta plus 1. So IE is equal to beta plus 1 times IB, and IB is equal to IE over beta plus 1. So substituting our values, we get 65.77 microamperes. The collector current is expressed as beta times IB. So this is going to be 7.23 milliamperes. The voltage across the BC junction is simply going to be this minus this, sorry, VBC. So starting from B going to C, I mean, yeah, B going to C is going to be 9.46 volts. Sorry, I forgot the letter V, minus 12 volts. So as you can see, it is negative 2.54 volts because using BC is going in the wrong direction of the current when it should be going this way. That's why it is negative 2.54. Make sure to include the negative sign in your final answer because without it, it will be considered wrong. Lastly, we have the voltage across the CE region. So since you already have VC and VE, we can just subtract them. I think I forgot to put it in the PowerPoint, but that should be 3.24. So this one is a common base. It just doesn't look like one because it is shaped differently. But if you see here, you can actually just connect this all the way back here, and this one connecting to here, and it's going to be a common base. Or you can just redraw it like this. So anyway, while I'm redrawing it, the emitter current is going to be VEE minus VBE all over RE. So it's like that because we start from VEE. Sorry, wait. The emitter current. Yeah. So we start from VEE minus VBE all over 2.2 kilo ohms. So take note, IE is equal to 3.32 milliamps because IE is going in this direction. You can check whether or not it should be positive or negative by looking at the ground. So if you don't know, um, this can sometimes complicate things, but it's easier if you just look at it. So you have 0 going to a negative 1. So naturally, if your IE is going in this direction, as indicated by this arrow, you expect that it is supposed to be positive. Yeah. So this is the formula for the voltage across the CE region. So in case you forgot it like I did, I had to type it out or write it out. So KVL of the perimeter, starting from VEE plus VCC minus the voltage drop here, minus the voltage drop here, and minus the voltage drop at the resistor here is equal to 0. So if you memorize the formula, you can just skip the rearrangement and go to this step. So VCE is equal to VEE plus VC, the two sources, minus the voltage drops across RE, sorry, RC and RE. So there is only one current here. That's why we can just group them into IE. So substituting all of that, we get VCE is equal to 4.72. Again, VCE must be positive because 10 volts is going down to negative 8 volts. Next, we have the emitter voltage. So VBE is equal to VB minus VE. So as we can see here, VE is around here. And this is 0 volts. So if 0 experiences a voltage drop of negative 0. Sorry, a voltage drop of 0.7, this part will be 0 minus 0.7 or simply negative 0.7. Lastly, we have the collector voltage. So VCE is basically just going from, yeah, so from C to E. Oh, wait, my bad. We are looking for the collector voltage. So using this formula, VCE is equal to VC minus VE. And we already know this is negative 0.7. We can just substitute. So 4.72 plus negative 0.7 is going to equal 4.02. So that's it for this common base configuration. So this is our very last item for this reviewer. We are to determine IB, IC, VE, and VCE. Now this looks like a voltage divider at first. In fact, it looks like the hardest one that we solved earlier, except there are two key differences. First one, that is the most obvious, this one is not at ground. And the second one, that is least obvious, there is no input voltage and there is no output voltage specified. So normally, uh, if we have a V in here and there's no specified input voltage, we usually treat it as a ground. But since there is no ground, again, since there is no ground this time, we have to take a different approach in computing for the Thevenin voltage and the resistance. So the resistance is still done as normal. We have 510 kilo ohms and 510 kilo ohms. You're going to notice that it's exactly the same. So their equivalent Thevenin voltage is going to be half at 255 kilo ohms. Next, their Thevenin voltage. Since there's no ground, we cannot use I the same way we did earlier. We cannot compute for the current and then multiply it to R sub 2. No. The way we are able to approach it now is to look at the averages. So looking at this and looking at this, we know that there are two voltage sources, plus 18 and plus 18. However, notice that this is going this way, and presumably this is going this way as well. So that's why the second 18 is still negative. So 18 volts minus 18 volts. Multiplying it to the voltage divider rule, we see that again, they are exactly the same. So it doesn't matter which one is our R1 and which one is our R2. And we end up having 0 volts. This makes sense because on one hand there is plus 18, the other hand there is negative 18. And then in the middle, if the resistances are equal, then it should make sense that this is 0 volts. So again, this is what appeared in the answer key. So now, the emitter current setup. This is different and the most difficult out of them so far because I could not find any information on how you can solve it without using algebra. I mean, algebraic manipulation, yes. So IE is equal to, so here, the current IE. IE is equal to this minus negative 18 all over 7.5 kilo ohms. So that becomes VE plus 18 volts all over um, 7.5 kilo ohms. So from here, we can rearrange some stuff. We know that VE is something that we need to get because we're trying to solve for the base current. I mean, no, wait. Let me rephrase that. VE is something that we need to substitute because we know that as we're solving for the base current, we can use VBE. So we need to find something that we can relate to. So VBE is equal to VB minus VE, and we arrange that to get VE is equal to VB minus 0.7 volts. So after solving this, um, it's still incomplete, but we can use it for now. So substitute VE and turn it into VB minus 0.7 volts. So our IE now is VB plus 17.3 volts all over 7.5 kilo ohms. Again, we still don't know what VB is, and we still don't know what IE is. So let's proceed. Okay, now for our base current. We know that the current across the base is going to be the voltage here minus the voltage here all over the resistance here. So that is ETH minus VB all over RB, or simply RTH. So we already have an established value for 0 volts and an established value for 255 kilo ohms. However, we cannot assume that IB, sorry, that VB is equal to ETH, at least not yet. So IB is gonna equal negative VB all over 255 kilo ohms. So we rearrange this, multiply both sides by 255 kilo ohms, and then isolate VB. So if this is negative, multiply both sides by negative 1, and you get VB is equal to negative 255 kilo ohms times IB. So now that you have this value, you can put it in here. So that's what we did. So now you also have to find a relation to IB. So since emitter current has the IB, and you know that IE and IB are related by beta plus 1, you can use IE is equal to beta plus 1 times IB. So basically, IE is equal to beta plus 1. So beta is 130 as given here, plus 1, multiplied by the value of IB. Now since we're trying to solve for IB, this will be our variable. So you can treat it like an x in algebra. So first multiply both sides by 7.5, and then you get this equation. Next, you can combine like terms. So you see 255 kilo ohms IB is present in both of these terms. So you move this to the other side. So 982.5 plus 255 is 1237.5 kilo ohms IB. So divide both sides by 1237.5 kilo ohms, and you should get 13.98 microamperes. So this is the hardest one so far. Look at how long our computation got, and we only got 1 out of 4 so far. So hope nothing like this appears in the exams, but just in case. Once you've solved for IB, and generally IB is the key to solving most of the things because of beta. So solving the currents, IC is equal to beta IB. It's 130 times what we solved in the previous slide is equal to 1.82 milliamperes. So now we are looking for VE. So VE is the emitter voltage, and we can't really compute for that yet. I mean, we can actually. Oh wait, we can't. Not yet. Because we still have IC. So I'm going to skip this first. I'm going to go here. IE is equal to IB plus RC. So you have IC here and IB from the previous slide. You can add that to get 1.83 milliamperes. So using that now, the emitter voltage, we know that IE is going to be 1.83 milliamperes in this direction. You have VE minus negative 18 here, all over 7.5 kilo ohms. So rearranging the formula, multiplying both sides by RE, and then isolating VE, you get VE is equal to IERE minus 18 volts. So VE is equal to negative 4.27 volts. Now, you need to check if it's supposed to be negative. So, negative 4.27. So, let's see. Negative 18 volts is going up. So, positive. Sorry. Wait. Okay. So, we're going to a less negative to a more negative. So, we're actually going in this direction. So, this is correct. It should be negative. Now, for the collector voltage. We need to get it because we are also asked to solve the voltage across the CE region. And to get the voltage across the CE region, we need to get VC, which we can find in here. So I use the collector voltage because we already have IC, we already have VCC, and we already have RC. So rearranging the formula first, we get VC is equal to VCC minus ICRC. And then that is equal to 144 1.44 volts. So this is 1.44 volts. Lastly, looking for the voltage across the CE region, if we already had the VE earlier of negative 4.27, then VCE is equal to 1.44 minus negative 4.27. Again, the negative signs should cancel out. They should become a plus together. So you can expect VCE is larger. So it is 5.71 volts. And that's pretty much it for BJTs. So thank you so much for watching, and I hope you enjoyed this video. And rest assured, all of the problems that we went to today should prepare you for the multiple BJTs because it's basically just the same concept except with an extra step. Like for example, for the Darlington configuration, you just have to multiply beta 1 and beta 2. For the RC and the direct coupling, you can just check the output voltage, which is basically VC most of the time, or in some cases VE. And the other multiple BJT configurations, which I can't remember at the moment, are basically just using the same concepts that I shared with you today. So again, thanks so much for watching and good luck with your examinations.